The first deep images came back, and the people who built the telescope went quiet. They were looking at the oldest light the James Webb Space Telescope had ever caught, from a time when the universe was only a few 100 million years old. The plan was simple. Find the faint, half-formed first galaxies. Instead, the pictures were crowded with galaxies that were too bright and far too grown up for how early this was. Some looked as heavy as the Milky Way, built in a sliver of time that should not have been long enough. A few researchers ran the numbers, got an answer that could not be right, and assumed they had slipped up somewhere. They had not. To make something that big, that fast, the early universe would have had to break one of its own rules. So either the rule is wrong, or something out there is. Picture a screen in a dim room, late at night, with a handful of astronomers leaning towards it. On the screen is a single patch of sky so small you could hide it behind a grain of sand held at arm's length. Inside that patch sit thousands of points of light. Almost all of them are galaxies. Some of that light has been traveling for nearly 14 billion years to reach the camera. The people in the room built this telescope to catch exactly that. The faint first glow of galaxies that switched on when the universe was barely getting started. So they hunt for the oldest, faintest specks in the frame. The specks are not faint. They are bright. There are too many of them, and several look far too finished for how early we are seeing them. One researcher later admitted the team's first thought was that they had made an error somewhere in the pipeline. The galaxies looked impossible, so the math had to be wrong. They went back through it. The math held. That is the strange thing about the James Webb Space Telescope. It was designed to see deeper into time than anything before it. And the first time it looked hard at the beginning of the universe, the beginning did not behave. Here is why bright is a problem. In space, looking far away means looking far back in time. The light leaving a distant galaxy takes so long to cross the gap that you see the galaxy not as it is, but as it was when the light left. Point the telescope far enough, and you're watching the deep past play out. These particular galaxies are being seen as they were only a few 100 million years after everything began. On the scale of the cosmos, that is the first few minutes of a very long life. A galaxy that young is supposed to be small. It has not had time to gather much. It has not had time to build many stars. It should be a faint smudge, still pulling itself together out of raw gas. What the telescope found instead were galaxies blazing with light, some of them carrying as much material as the grown galaxy we live in today. The Milky Way took most of the age of the universe to become what it is. These objects look like they had pulled off the same feat in a fraction of the time. Picture a newborn that somehow shows up already adult. That is the size of the wrongness here. For a while, the easy move was to assume the telescope was being misread. New instrument, new tricks, easy to fool yourself. But the same kind of object kept turning up in image after image, survey after survey, in patches of sky the telescope had never pointed at before. A single mistake does not repeat itself that cleanly across the whole sky. So the people who study the early universe found themselves holding a question they did not want. Either they were misjudging what they were looking at, in some way they had not yet caught, or the universe had built something far bigger, far faster than the rules of physics say it could. That question does not go away in this story. It gets worse. Every time someone seems to close it, the telescope opens it wider. To understand why it shakes people so badly, you first have to know what they expected to see when they aimed at the dawn of time, because they had a very specific picture in mind. And it was beautiful, and careful, and almost entirely undone by a single patch of sky. Before the telescope launched, astronomers were not guessing. They had spent decades building a detailed picture of how the early universe should look, and they were excited to finally test it. The picture went like this. In the beginning, the cosmos was a smooth, hot fog. As it expanded and cooled, tiny ripples in that fog began to pull together under their own gravity. The very first stars lit up in the dark, alone or in small groups. Then those stars gathered into the first small galaxies, faint and blue and ragged, still stitching themselves together. Over time, these little galaxies would crash into each other and merge, growing larger with each collision, until after billions of years you ended up with the grand spiral and elliptical galaxies we see around us now. So when they aimed the James Webb Space Telescope at the earliest moments it could reach, they expected to catch that ragged opening act. Small clumps, dim light, galaxies caught in the middle of being born, awkward and unfinished. The whole reason to build a telescope this powerful was to finally see those first faint pieces and watch the building begin. The expectation was not a hunch. It came from the best model we have of how the universe works, a model that has passed test after test for decades. It correctly predicts the leftover heat from the Big Bang, glowing evenly across the whole sky. It correctly predicts how galaxies are spread through space, clustered in vast webs and threads. It correctly predicts the mix of the lightest chemical elements that came out of the first few minutes of creation. This is not a shaky idea. It is one of the most successful descriptions of reality that science has ever produced. And that model carried a clear schedule. The first real galaxies should not have grown massive quickly. There was a pace to it, set by gravity and by how much raw material was lying around to work with. You build slowly because building is slow. The universe had a speed limit on how fast structure could pile up, and everyone trusted that limit because everything else the model predicted had come true. So the people pointing the telescope were not bracing for a shock. They were looking forward to a confirmation. They thought they would see the faint beginning their equations had described, snap a few pictures of the cosmic dawn, and add another success to a long winning streak. This matters because it tells you how solid the ground was that just cracked. The galaxies that turned up were not breaking some flimsy assumption that nobody believed in. They were breaking a prediction that came straight out of our deepest, most tested understanding of how the universe assembles itself. When something that reliable gives you the wrong answer, you have two choices. You can decide you have misread the data, or you can start to wonder whether the schedule itself is wrong. To feel the weight of that second possibility, you have to understand the schedule in detail. You have to know what was supposed to come first, and second, and how long each step was supposed to take, because the whole problem comes down to a clock. And once you see how that clock was built, you start to see exactly where it appears to have skipped. Run the universe forward from the start and the order of events is fixed. It has to happen in steps, and each step waits on the one before it. It opens with almost nothing to look at. A scorching, even haze of particles spread out so smoothly that there is barely anything to grab onto. Then comes the first hidden player in the story. Most of the matter in the universe is not the ordinary stuff that makes up stars and planets and people. It is something we cannot see. Something that gives off no light at all. We only know it is there because of how its gravity pushes everything else around. We call it dark matter, which is an honest name, because dark is most of what we know about it. Dark matter does not glow, but it does pull. In the early haze, it was the dark matter that first began to clump. It gathered into invisible knots, then into larger lumps, then into great rounded clouds that scientists call halos. These halos were the scaffolding. They came first, and everything visible was built on top of them. Once a halo formed, its gravity reached out and dragged in the ordinary gas drifting nearby. That gas, mostly hydrogen, fell inward and began to pile up at the center of the halo. As more gas crowded in, it grew dense and it grew warm, and eventually pockets of it collapsed hard enough to ignite. Stars switched on. A galaxy began to glow inside its dark cradle. Then came the slow part. A young galaxy does not simply keep growing in peace. The bigger stars it makes burn fast and die in enormous explosions. Those blasts blow hot gas back out into space, scattering the very material the galaxy needs to build its next stars. The galaxy partly wrecks its own supply line, so star birth sputters. It happens in fits, never as fast or as complete as you might imagine, because the galaxy keeps interrupting itself. This is the heart of the schedule. Building stars is not just about having gas. It is about how much of that gas you can turn into stars before the process chokes itself off. And the answer, in galaxy after galaxy that we have studied up close, is not much. Only a small slice of the available gas ever becomes stars. The rest gets heated, blown away, or simply never gets the chance. So the expected story of the early universe is a story of patience. Dark matter clumps. Gas falls in. Stars flicker on, then partly snuff themselves out. Small galaxies inch toward becoming larger ones. And the only way to grow truly massive is to do this over and over for a very long time, merging with neighbors, gathering fresh gas, surviving your own violence, across hundreds of millions and then billions of years. That long, patient climb is what makes a galaxy as heavy as the Milky Way. And that climb takes time the early universe simply had not had yet. Which brings us to the wall. There is a hard limit built into this whole picture, a ceiling on how big a galaxy can possibly be at a given moment in cosmic history. It is not a guess or a preference. It comes straight from counting the raw material available. And the galaxies the telescope found were pressing right up against that ceiling, in some cases looking like they had punched clean through it. The ceiling is the part of this story that decides everything, so it is worth slowing down on. It comes from a simple act of counting. Start with one of those invisible halos of dark matter. It has some total mass, set by how much dark matter is clumped together in that spot. Now, the ordinary matter, the gas that can actually form stars, did not arrive in unlimited supply. In the early universe, for every unit of all the matter there is, only a small share is the normal kind. The rest is dark. The split is roughly 1 part normal matter for every 5 parts dark matter. So when a halo pulls in gas, it can only ever pull in about 1 part in 6 of its own weight as ordinary, star-making material. That is the entire grocery budget. There is no more on the shelf. Already that caps things. A halo of a given size simply cannot contain more normal gas than that fraction allows. But it gets tighter because gas is not stars. Having the gas is only the first step. You then have to turn it into stars, and as we saw, galaxies are terrible at this. They waste most of their gas. In the galaxies we measure carefully, only a few % of the available gas ever ends up locked into stars. The rest is blown out or left drifting. So now you have 2 limits stacked on top of each other. First, a halo can only gather a sliver of normal matter to begin with. Second, only a sliver of that sliver normally becomes stars. Put those together and you get a firm number for the most massive a galaxy can be inside a halo of a given size at a given age of the universe. That number is the ceiling. And the galaxies the telescope found were sitting at or above it. To explain their light as ordinary stars, you needed one of two uncomfortable things to be true. Either the halos were far larger than the model says they could have grown by that early time, meaning more dark matter had clumped faster than the schedule allows, or the halos were normal, but the galaxies inside them had converted nearly all of their gas straight into stars, with almost no waste at all. Take that second option seriously for a moment. It would mean an early galaxy grabbed essentially every scrap of gas it could reach and turned almost the entire amount into stars, running at near perfect efficiency. No real galaxy we have ever studied behaves anything like that. It would be like a factory that loses nothing, scraps nothing, and ships every gram of raw material out the door as finished product. In the messy, explosive, self-sabotaging life of a galaxy, that is not supposed to be possible. That is what people mean when they say the telescope may have found something bigger than physics allows. They do not mean the object is large in plain size. They mean it appears to carry more stars than the available matter and the available time should be able to produce. It is heavier than the budget permits. So the stakes are now clear. If these galaxies really are as massive as they first looked, then either dark matter built its scaffolding far faster than we believed, or the first galaxies were impossibly good at making stars, or our count of how much matter there even is has a hole in it. Any of those would crack the model, and the first hard evidence that one of them might be true arrived in the form of 6 galaxies that should not have been there. The 6 galaxies came out of one of the telescope's early surveys, and they landed like a punch. A team led by an astronomer named Ivo Labbé, working with a colleague named Joel Leja, was combing through the new images, measuring the light of distant galaxies. 6 of them stopped the team cold. By the team's first measurements, these galaxies were being seen as they were only 500 to 800 million years after the universe began. And yet each one appeared to hold billions of times the mass of our sun in stars. One of them looked like it might carry as much as 100 billion times the sun's mass. That is in the same league as the fully grown Milky Way, the product of nearly 14 billion years of building, somehow already assembled in the cosmic equivalent of early childhood. Leja later put it bluntly. The finding, he said, upended what many researchers had thought was settled science. The team started calling these objects the universe breakers, half as a joke and half because the name fit. 6 points of light that, taken at face value, did not fit inside the ceiling. The honest reaction inside the team was disbelief. Labbé said they did not think the results were real at first. There simply could not be galaxies as mature as the Milky Way that early in time. The objects looked so big and so bright that some members of the group assumed they had slipped up somewhere. They went back to the data expecting to find their own mistake. They did not find it. The galaxies stayed stubbornly large. Now, the team was careful, and that care matters. They did not announce that the universe was broken. They called these objects candidates. They knew their measurements rested on a first pass, on the brightness and colors of the light, and they said openly that the masses still needed to be confirmed by closer study. Leja noted that a few of the objects might turn out to be something other than ordinary galaxies. Maybe not all 6 would hold up, but even with that caution, the implication hung in the air. If even one of these, especially one of the truly massive ones, turned out to be exactly as heavy as it looked and as early as it looked, that one object alone would be a serious problem. You only need a single galaxy too big for its moment to show that the schedule has a flaw. The model does not get to be mostly right about the impossible. One real universe breaker breaks it. So the field split into the work that always follows a shock like this. Some researchers raced to confirm the distances and masses. Others started asking what could possibly be wrong with the measurement, looking for the loophole that would let the universe off the hook. And a few began quietly wondering whether the schedule needed rewriting, whether galaxies in the early cosmos had grown in some faster way we had never modelled. All of that hinged on a deeper question, one we have been leaning on this whole time without examining. How do they actually know how far away these galaxies are, and therefore how early we are seeing them? Because if the distances were wrong, the whole crisis would evaporate. Everything depends on a single measurement, written into the color of the light itself. The measurement is called redshift, and once you understand it, a lot of this story clicks into place. Light travels as a wave, and a wave has a length, the distance from one crest to the next. That length is what your eye reads as color. Shorter waves look blue, longer waves look red. Stretch a wave of light out and you slide its color towards the red end. Stretch it far enough and it slips out of visible light entirely and into the infrared, the kind of light we feel as heat rather than see. Now here is the key fact. The universe is expanding, not the galaxies flying apart through space, but space itself swelling, carrying everything along with it. While a beam of light is crossing the vast gap between a distant galaxy and us, the space it is traveling through keeps stretching. And as that space stretches, it stretches the light wave riding through it. The longer the journey, the more stretching, the redder the light arrives. You have heard a version of this with sound. A siren rises in pitch as the ambulance races toward you and drops as it speeds away, because the sound waves get squeezed or stretched by the motion. Light does something similar, except here it is the swelling of space itself, doing the stretching over billions of years. So the amount of reddening tells you how long the light has been traveling. A little stretch means a nearby galaxy whose light is fresh. A large stretch means an ancient galaxy whose light set out when the universe was far younger and far smaller. Astronomers fold all of this into a single number they call the redshift. A high redshift is a badge of extreme age and distance. The galaxies in this story carry some of the highest redshifts ever measured. Their light left when the cosmos was a tiny fraction of its current size. That stretching is also why the James Webb Space Telescope had to be an infrared telescope. The first galaxies gave off ordinary visible and ultraviolet light, but that light has been stretched so hard on its way here that by the time it reaches us, it is no longer visible at all. It has become infrared. Earlier telescopes that watched in ordinary light were nearly blind to it. This telescope was built specifically to catch that stretched, reddened, ancient glow. That is its whole reason for being. There are two ways to read the redshift, and the difference between them runs through the rest of this story. The quick way is to measure the galaxy's brightness through a set of color filters and estimate the stretch from how the colors line up. It is fast, and it lets you survey thousands of galaxies at once, but it is an estimate. The careful way is to spread the galaxy's light out into a full spectrum, a fine band of all its colors, and read the precise fingerprints in it. That pins the redshift down for real. The early universe breaker masses came mostly from the quick way. The distances looked extreme and the brightness looked extreme, and from those the masses were estimated. But notice what that means. We never measured the mass of these galaxies. We measured their light and we calculated the rest. And calculation is only as good as the assumptions you feed it. Change one assumption about what is making the light, and the whole answer can move. That gap between what we see and what we infer is where the real trouble lives. The telescope does not measure mass. It measures light. Everything else is a conclusion drawn from that light. And conclusions can be wrong in ways the raw light never is. Think about how you would weigh a city from very far away, at night, with no way to fly closer. You cannot count the people. All you can see is the glow of its lights. So you make an assumption. You decide that a certain amount of glow means a certain number of people, based on cities you know well. Then you measure the glow and multiply. If your assumption is good, your estimate is good. But if this particular city is lit up in a way you did not expect, your number could be far off, and you would never know just by staring at the brightness. Weighing a distant galaxy works almost exactly like that. You measure how much light it sends you. Then you assume that the light comes from a normal mix of stars, the kind of mix we see in galaxies nearby. From that assumed mix, you work out how much mass it would take to produce that much glow. Multiply, and you have your estimate of the galaxy's mass in stars. The whole result rides on that one assumption about what is making the light. And in the early universe, that assumption is exactly the thing we are least sure about. We have never seen these galaxies up close. We do not actually know that their stars come in the same mix as the stars around us. We do not know that all of the light even comes from stars at all. We are weighing a city we have never visited, using a rule book written for cities on the other side of time. So when the universe breakers came back looking impossibly heavy, careful researchers did not only ask whether the universe was broken, they asked a sharper question. What if the assumption is what is broken? What if these galaxies are pumping out far more light per unit of mass than we expected, so that they only look as heavy as the Milky Way, while actually carrying far less? There are real ways that could happen. Maybe the early stars were unusually bright for their weight, squeezing out more glow than the same mass of ordinary stars would. Maybe a small amount of material, arranged in an extreme way, was masquerading as a vast population of stars. If the light is cheaper to make than we assumed, then the mass shrinks, and the galaxy slides back under the ceiling, and the crisis softens. This is not a way of wishing the problem away. It is the most important move in all of science, which is to doubt your own measurement before you tear down the laws of physics. Before you announce that the universe runs on a broken clock, you make absolutely sure you are not just reading the dial wrong. But doubt cuts both ways. The assumption could be wrong in the direction that makes things heavier instead of lighter. And the only way to stop arguing about assumptions is to stop estimating and start measuring directly, to pull these galaxies' light apart and read what it is actually made of. That is the difference between a candidate and a confirmed object. And almost everything in those first headlines was still only a candidate. A candidate galaxy and a confirmed galaxy are not the same kind of fact. And the distance between them is where a lot of these stories quietly rise or fall. When astronomers first spot one of these distant objects, they usually have a photograph. Not a single picture, but a set of pictures taken through different color filters, each one letting through a narrow band of light. By comparing how bright the object looks in each band, they can estimate its redshift and its mass. This is fast and powerful. It lets them sift through thousands of faint smudges and flag the interesting ones. But it is a guess dressed in numbers. The colors point toward an answer. They do not prove it. The trouble is that very different objects can wear similar colors. A genuinely ancient distant galaxy can look, through a set of filters, a lot like a closer, dustier galaxy whose light has been reddened by other means. From a handful of brightness measurements, you cannot always tell the ancient giant from the nearby imposter. So a photograph alone leaves room to be fooled, sometimes badly. The cure is a spectrum. Instead of catching the galaxy's light in a few broad color bins, you spread it out into a full, fine rainbow, a continuous band running from one end of the light to the other. Woven into that band are sharp lines, bright and dark stripes at exact positions. Those lines are fingerprints left by specific chemical elements, each glowing or absorbing at its own precise color. They are the closest thing the universe has to a signature. Those fingerprints do two things at once. First, they nail the redshift. Because we know exactly where each element's lines sit when the light is fresh, we can measure how far they have all slid toward the red and read off the stretch with real precision. No more estimate, a hard number. Second, the pattern of lines tells you what is actually glowing. Whether you are seeing the light of ordinary stars or the fierce glow of gas spiraling into something far stranger. This is why the first universe breaker announcements came wrapped in caution. They rested mostly on the photographs. The teams said so plainly. They called the objects candidates and said the masses needed confirmation through the slower, harder work of taking a full spectrum of each one. That work takes precious telescope time, and you can only point at one tiny target at a time. So a real gap opened between the headline and the proof. The headline said the universe might be broken. The fine print said, "We will know once we read the fingerprints, and that will take a while." And while that work was underway, the field did the responsible thing. It kept testing. Teams went back over the same patches of sky with sharper methods. They checked whether the distances held. They checked whether the masses survived a harder look. They asked whether some of these giants might be hiding something other than a crowd of stars. When that closer look finally came back, it did not simply confirm the panic, and it did not simply end it. It split the problem in two. Part of the crisis shrank, almost with relief, and part of it refused to shrink at all, and in fact got stranger. The giants were about to change shape in front of everyone. The closer look came, and at first it sounded like good news for the standard picture. A study led by a graduate student named Catherine Chworowsky, working with data from one of the telescope's deep surveys, went back to the early galaxies and weighed them more carefully. Her conclusion was steadying. Some of those early galaxies, she found, were in fact much less massive than they had first appeared. None of them, by her team's reckoning, were so heavy that they truly broke the universe. The most frightening reading of the data, the one that demanded near-perfect star-making, eased. Her own words were almost reassuring. She said they were still seeing more galaxies than predicted, but none so massive that they shattered the model. The ceiling, it seemed, had bent without snapping. And the reason the giant shrank is the thread that pulls the rest of this story along. In some of these galaxies, the light was not coming purely from stars. Part of the glow was coming from the center, from material falling towards something extraordinarily dense and being heated to a furious shine on its way in. That central glow was inflating the brightness, making the galaxies look bigger and heavier than the stars alone could account for. Subtract the misread light, and the stellar mass drops back towards something the model can live with. So one version of the crisis softened. The early universe was probably not stuffing impossible mountains of stars into tiny windows of time. We had partly been fooled by extra light from the cores, but notice that the relief came at a price. To make the masses behave, you had to admit that something was burning at the centers of these galaxies. Something that was not stars. Something pouring out enough light to throw off the count. You did not make the mystery vanish. You traded one mystery for another and called it progress. And even after that trade, the books did not fully balance. Chworowsky's own work left a smaller but stubborn problem standing. Even with the masses corrected, there were still far too many massive galaxies in the early universe, roughly twice as many as the model predicted should exist that early. The worst case had eased, but the universe was still being too generous, too quickly, with big galaxies. The ceiling had stopped looking shattered. It still looked cracked. This is the rhythm you start to feel in this whole field. Every time someone seems to close the gap reopens a little further down. Make the giants lighter, and you are left with too many of them. Explain the extra light, and you have to confess that black holes are blazing where they should not yet exist. The main question, how the early universe built so much so fast, does not get answered. It just changes outfits. And the new outfit was the more interesting one by far. Because in correcting the masses, astronomers had been forced to take seriously a population of objects they had barely noticed at first. Tiny, red, scattered all through the early universe in numbers no one had expected. They were hiding in plain sight in the same images that held the universe breakers. People started calling them the little red dots, and almost nothing about them made sense. The little red dots earned their name honestly. In the images, that is exactly what they are. Small, red, round points of light, so compact they look less like sprawling galaxies and more like single stars sitting in the deep field. At first they were easy to overlook. The eye goes to the big dramatic universe breakers, not to a scatter of tiny red specks. But as teams work through survey after survey, the deep imaging programs with names that just mean different patches of carefully studied sky, the same kind of object kept showing up. Compact, reddened, and common. Not a handful of oddities, but a whole population, turning up again and again across the early universe, seen as they were from roughly 600 million to about 1.5 billion years after the beginning. That abundance was the first surprise. You do not expect to discover an entirely new and numerous class of object in a universe we thought we understood. These were not predicted. Nobody had a slot waiting for them. They simply appeared in the data in large numbers the moment we had a telescope sharp enough to pick them out. The second surprise was the redness itself, and how strange it was. A galaxy can look red for ordinary reasons. It can be full of old, cool stars. It can be wrapped in dust that filters out the bluer light. But the little red dots did not fit the easy explanations cleanly. Their light had a peculiar shape to it, blue in some respects, and steeply red in others, as if two very different things were glowing at once inside the same tiny point. And the third surprise was the size. These objects are extraordinarily compact. Whatever is producing all that light is crammed into a tiny region, far smaller than a normal galaxy spreads its stars across. You are seeing a great deal of light pouring out of a very small space. Put those together and you have a genuine puzzle. A new, abundant kind of object, deep in the early universe, glowing brightly out of a tiny volume, with a color no simple story fully explains. For a while, the most natural guess was that these were just very dense early galaxies, packed with stars. And if that were true, they would be part of the same crisis as the universe breakers. More mass than the early universe should be able to assemble, squeezed into an even smaller box. That reading would have made things worse. A normal galaxy that heavy is already a strain on the model. A galaxy that heavy crushed into a space that's small is a deeper strain still. But as astronomers managed to take spectra of some of these dots, to read the fingerprints in their light, the picture began to shift in a direction nobody had quite expected. The light did not look like a calm crowd of stars. It looked like motion. It looked like gas moving at tremendous speed, glowing as it was whipped around and heated by something hidden at the center. And that pointed to a culprit that changes the whole nature of the problem. The little red dots might not be galaxies stuffed with stars at all. The light might be coming from gas falling toward a black hole, and not a modest one. So here is the turn. For much of this story, we have been asking how the early universe packed so many stars into so little time. The little red dots suggest that, at least for them, the answer is that it may not have been stars at all. When the spectra came back, the signature in many of these objects looked like the glow of an active center. Picture gas spiraling down toward a black hole. As it falls, it crowds together, speeds up, and heats to a ferocious temperature, blazing with light before it disappears over the edge. That kind of glowing and rush has a recognizable look. Wide, fast-moving gas, a fierce central source, and crucially, it can outshine all the stars in a galaxy from a region barely larger than our own solar neighborhood. That single idea cleans up several mysteries at once. It explains why the dots are so compact, because the light is coming from a tiny central engine rather than a spread-out swarm of stars. It explains the strange split in their color, with different processes glowing in different parts of the light. And it explains why some of the early galaxies look so impossibly massive. We have been counting the blaze of these central engines as if it were starlight, and starlight is what we converted into mass. Take the engine out of the equation, and the inflated masses deflate. If you want to follow this story as it keeps breaking, subscribing keeps you in the room for it. Now, you might think, this is the moment the crisis ends. If the extra light comes from black holes and not from impossible crowds of stars, then the galaxies are lighter, the ceiling holds, and we can all relax. It is the opposite. Trading impossible galaxies for these black holes does not calm the situation. It hands you a worse one. Because a black hole big enough to outshine an entire early galaxy is not a small thing. To pour out that much light, the central object has to be enormous, weighing in at millions, in some cases far more, times the mass of our sun. And we are seeing these monsters in the first billion years of the universe, sometimes much earlier. They are already huge, already gorging, already blazing, at a moment when, by the schedule, there should not have been anywhere near enough time to grow something that big. So, the question does not close. It moves. We started by asking how the early universe built galaxies too massive too fast. Now we are asking how it built black holes too massive too fast. We swapped one impossible giant for another. And the new giant might be even harder to explain than the first. Because at least a galaxy can grow by merging and gathering over time. A black hole has its own strict speed limit on how fast it can grow, set by the very light it gives off. And when you do the arithmetic on these early monsters, the time does not add up. It gets worse before it gets better. Because these black holes are not only too big for the early universe, they are too big for the galaxies they live in. There is a rule about black holes and the galaxies that host them, and the little red dots appear to be breaking it. In the universe nearby, almost every large galaxy has a giant black hole sitting at its center, and the two go together in a remarkably steady way. The bigger the galaxy, the bigger its central black hole, and the ratio between them stays fairly fixed from one galaxy to the next. A galaxy like ours holds a central black hole of a certain weight, and that weight is a tiny predictable fraction of all the stars around it. It is one of the cleaner patterns in astronomy. Galaxies and their black holes seem to grow up together, locked in step, each one's size reflecting the others. That lockstep is not just a curiosity. It is a clue that galaxies and their black holes shape each other as they grow. trading material and energy in a long shared history. The fixed ratio is the fingerprint of that partnership. The little red dots tear that fingerprint up. In these objects, the central black hole appears to be wildly, absurdly heavy compared to the galaxy around it. Not a little over. We are talking about black holes that look 10 to 100 times too massive for the modest collection of stars they sit inside. The partnership is broken. The black hole has raced far ahead of its galaxy, ballooning to a size that, in the nearby universe, would require a galaxy many times larger to match. Astronomers have a flat name for these: overmassive black holes. Black holes that have outgrown their homes. Sit with how strange that is. In the universe we know, a black hole that big means a galaxy that big. The two come together. But here, at the dawn of time, the rule runs backwards. The black hole is already a monster while the galaxy around it is still small. It is as if the heart of the thing grew to full size before the body had a chance to. And this is not one freak object. The little red dots are abundant, remember? If a good fraction of them really are overmassive black holes, then this is not a fluke. It is a pattern. The early universe seems to have been very good at making enormous black holes very quickly, far better than it should have been, and far better than it would later become, since the lockstep rule holds tightly in galaxies near us today. So the mystery has sharpened to a fine point. It is no longer just that the early universe built too much, too fast. It is that the very first things it rushed to build were these black holes, growing ahead of schedule and out of proportion, leading their galaxies instead of following them. Which forces the hardest question yet. Forget the galaxies for a moment. How do you grow a black hole that big, that early, at all? Because a black hole cannot simply will itself to swell. It grows by eating. And eating, it turns out, has a strict speed limit, one written into the laws of physics. And by that limit, these monsters should not exist. A black hole grows by swallowing matter, and you might assume there is no limit to how fast it can eat. There is. And that limit is the wall this whole story keeps running into. When matter falls toward a black hole, it does not drop in quietly. It piles up in a swirling disk, crushes together, and heats to a blistering glow. That glow is light, and light pushes. It presses outward on the very gas that is trying to fall in. Feed the black hole too fast, and the outward push of all that radiation grows strong enough to shove the incoming gas back, choking off the supply. The black hole, in effect, blows away its own meal. So there is a natural ceiling on how fast a black hole can grow by feeding, set by the balance between gravity pulling matter in and the light of the feeding pushing matter out. Past that rate, the process stalls itself. This limit has a name in the field, but the idea is simple. A black hole can only bulk up so quickly, no matter how much food is around, because its own brilliance gets in the way. Now, run the clock. The standard story for how these black holes began is that they grew from seeds left behind by the very first stars. When a massive early star dies, it can collapse into a black hole, weighing perhaps a few tens or hundreds of times the mass of our sun. That is the seed. Then it feeds and grows as fast as the speed limit allows. Here is the problem. Start from a seed that's small, grow it as fast as the laws of physics permit, and you still cannot reach the size of these early monsters in the time available. The universe is only a few 100 million years old when we see some of these overmassive black holes already weighing millions of times the sun. There has not been enough time. Even running the engine flat out with the throttle pinned at the maximum safe rate the entire time, you fall short. The seed is too small and the clock is too short. It is like being told that a sapling, growing as fast as any tree can grow, became an ancient redwood in a single season. The growth rate is capped. The time is fixed. The endpoint is impossible to reach from that starting point. Something in the story has to give, and this is not a fringe complaint. It is one of the central open mysteries in the study of the early universe. The black holes are there. We see their light. We measure as best we can their weight. And the most natural way to make them, by growing tiny seeds at the maximum rate, cannot produce them in time. The arithmetic simply refuses to close. So researchers are left with a stark choice, the same shape of choice that has haunted this whole story. Either there is something wrong with how we think black holes feed and grow, or the black holes did not start small at all. That second option is where the field has increasingly turned. Maybe these giants were not grown from the ashes of single stars. Maybe they were born heavy, skipping the slow climb entirely, arriving in the universe already enormous, and the ideas for how that could happen are strange enough to be their own kind of revelation. If a black hole cannot grow fast enough from a small seed, then maybe it never was small. Maybe it started heavy. That single shift in thinking has opened one of the most active frontiers in the study of the early universe, and the leading ideas are genuinely strange. The frontrunner is a process people call direct collapse. Picture a vast cloud of pristine gas in the early universe, far more than enough to make a star. Normally that gas would cool, break into clumps, and fragment into many ordinary stars. But under the right rare conditions, the gas does not fragment. Instead, the whole enormous cloud collapses more or less in one piece, skipping the stage of becoming a crowd of stars entirely, and folding straight down into a single black hole that is born already weighing tens of thousands, even hundreds of thousands of times the mass of our sun. That is the appeal. A seed that heavy does not need the impossible growth. It starts most of the way there. Give it a head start that large, and the speed limit on feeding is no longer a death sentence. It can reach the monsters we see in the time we have. The catch is that direct collapse needs a delicate setup. The gas has to stay smooth and avoid breaking into clumps, which usually means it has to be kept warm enough not to cool and fragment, often by a flood of radiation from somewhere nearby. The conditions are fussy and rare. Whether they happened often enough, early enough, to seed the whole population of overmassive black holes we are now finding is very much an open question. It is a leading idea, not a settled fact. And it is not the only one on the table. Some researchers propose that the first stars themselves could grow to truly monstrous sizes in the early universe, far larger than stars today, and leave behind heavier seeds when they died. Others suggest that in the dense, crowded hearts of the first star clusters, black holes could pile onto one another, merging and feeding in a runaway that builds a giant fast. Each of these is a way to cheat the clock, to arrive at a huge black hole without the slow grind that the simple picture demands. What they all share is an admission. The straightforward story does not work. To explain what the telescope is showing us, the early universe had to do something special, something faster and more extreme than the gentle schedule allowed. The debate now is only over which extreme thing it did. So step back and see where we have arrived. We started with galaxies that looked too massive too early. We learned that some of that mass was an illusion, light from black holes mistaken for stars. And chasing that illusion led us to black holes that are themselves too massive too early, breaking the rule that ties them to their galaxies, demanding to have been born already huge. The crisis did not resolve. It burrowed deeper, from the galaxies into their hidden cores. And just when the field was wrestling with all of this, the telescope did the one thing guaranteed to make everything harder. It looked even farther back. It found something even earlier. And what it found there did not just sit at the edge of the possible. It sailed past it and was confirmed beyond any argument about candidates and assumptions as real. The new object did not arrive as a candidate. It arrived as a fact. Astronomers gave it a working name, MOEM Z14, the number marking just how far its light has been stretched. And the stretch is staggering. We are seeing this galaxy as it was only 280 million years after the universe began. To put that in scale, if you compressed all of cosmic history into a single year, this light left in the first week of January. It is the closest look at the dawn we have ever managed. What sets it apart from the universe breakers is that no one has to argue about it. The early giants rested on photographs, on colors run through filters, on estimates that could be challenged. This one was pinned down the hard way. A team spread its light into a full spectrum and read the fingerprints directly. The lines were there, sharp and unmistakable, sitting exactly where an object at this enormous distance should put them. The distance is not a guess, it is measured. That is why the team that confirmed it reached for an unusually bold word. They titled their work around the phrase, "a cosmic miracle." Scientists do not throw that word around. They used it because, by the schedule we have been following this whole story, a galaxy this bright, glowing this clearly, this soon after the beginning, sits right at the edge of what should be possible. And unlike the earlier giants, it cannot be waved away as a measurement error. The spectrum closes that door. Think about what the universe was like at the moment this light departed. The first stars had only recently begun to switch on. The cosmos was a small, dense, still cooling place. There had barely been time for anything to organize itself. And yet, here is a galaxy already bright enough that a telescope, peering across nearly the whole age of the universe, can not only detect it but break its light apart and study its chemistry. The discovery also reset the record books in a way that tells you how fast this frontier is moving. For years, the most distant galaxy anyone knew was a single famous object that an earlier telescope had spotted. A lone hint that the early universe might hold surprises. That record holder is now not even in the top 10. The James Webb Space Telescope has found galaxy after galaxy beyond it, pushing the frontier back again and again, and this one stands, for now, at the very edge. For now is the phrase that hangs over all of it. The team behind this discovery did not present it as a final answer. They said the opposite. They wrote that the telescope appears poised to push the frontier further still, that distances once thought unreachable, close to the era of the very first stars, no longer feel far away. They expect this record to fall. They expect to keep finding things this early or earlier. So we have crossed from argument into certainty, and the certainty is unsettling. The earlier giants might have been misread. This one was read precisely, and it is still too much, too bright, too soon. And once you accept that this galaxy is real and this early, the next thing you want to know is what it is actually like up close. How big is it? How does it shine? Because the answers to those questions are where it stops being merely a record and starts being genuinely strange. The strangeness starts with its size, because it is tiny. You would expect a galaxy bright enough to spot across nearly the entire universe to be huge, a sprawling city of stars. This one is the opposite. Measured across, the glowing part of it spans only a couple hundred light years. Set that against the galaxy we live in. The Milky Way stretches roughly 100,000 light years from edge to edge. This early object is something like 1% of that width. It is a pinprick by Comptocatic standards, a dense little knot of light. And out of that pinprick pours an enormous amount of brightness. That is the unsettling part. Take a vast amount of light and cram its source into a tiny volume, and you are looking at something extreme. The stars, or whatever is shining, must be packed together at a density that makes our own crowded galactic center look sparse. This is not a gentle, spread out glow. It is concentrated, fierce, and small. There is another oddity, and it cuts against the object's very name. The little red dots from earlier were red in part because of dust, or so the simplest reading went. This galaxy is not dusty. Its light comes through clean. In the early universe, dust is supposed to take time to build, because the heavy elements the dust is made of have to be forged inside stars, and then scattered when those stars die. A galaxy this young has had almost no time to make dust. And sure enough, this one looks remarkably free of it, its light undimmed and clear. That clean light is a gift and a problem at once. A gift, because it means we are seeing the galaxy more or less as it truly is, not through a haze. A problem, because a bright, dust-free, tightly packed galaxy this early is exactly the kind of object the standard schedule struggles to produce. There simply has not been time to build a dense, blazing knot of stars at this point in cosmic history. Not by the patient process we walk through. Hold the picture in your mind. A speck of a galaxy, a tiny fraction of the size of our own, shining with the brightness of something far larger, its light clean and sharp, sitting at the very edge of the observable past. Everything about it is concentrated. Everything about it is early. And everything about it pushes against the idea that the first galaxies were faint, ragged, half-formed things still waiting to grow up. It is as if you went looking for the first faint sketch of a galaxy and found instead something already drawn in hard, bright lines, and brightness and size are only the outside of the object. The deeper surprise is hidden inside its light, in the fine pattern of fingerprints that the spectrum revealed. Because when the team read those lines, they did not just confirm the distance, they read the galaxy's chemistry. They found out what it is made of. And what it is made of points to something we did not expect to be witnessing this early. A kind of star formation that, until now, we'd only seen frozen in the ancient relics scattered through our own galaxy's outskirts. The fingerprints in the light carried a chemical surprise, and it links this distant speck to some of the oldest objects in our own backyard. When the team read the spectrum, they found a strong signature of nitrogen, and that on its own is odd. Nitrogen is not one of the first elements you expect to see in such quantity so early. More striking was the balance. There was far more nitrogen relative to carbon than you find in ordinary settings. The galaxy was rich in one and comparatively short on the other. An unusual recipe that does not come from just any kind of star formation. We've seen this particular recipe before though, not in distant galaxies, but close to home, locked inside objects called globular clusters. A globular cluster is a tight ball of hundreds of thousands of stars, bound together and orbiting the outskirts of galaxies like ours. The ones around the Milky Way are ancient, among the oldest things we can study, relics from the early days of our own galaxy's formation. And many of them carry exactly this chemical fingerprint, this same overabundance of nitrogen. So the distant galaxy and the ancient clusters in our own sky seem to share a chemical signature. That is a thread stretching across nearly the whole history of the universe, tying something we see at the very edge of the past to something we can study in detail right next door. The leading reading of that thread is remarkable. The chemistry suggests we may be watching, in real time, the birth of the kind of dense, tightly bound star clusters that would go on to become the ancient globular clusters we still see today. We might be catching the early universe in the act of forging the very objects that have survived, scattered and aged, all the way to the present. The peculiar nitrogen could be the byproduct of huge, short-lived stars crowded into a dense cluster, enriching their surroundings before they died. That would explain a great deal. It would explain why the galaxy is so small and so dense, because a forming star cluster is exactly that, a compact knot of stars packed tightly together. It would explain the fierce, concentrated brightness, and it would connect galaxy formation across the entire sweep of time, from the first few 100 million years straight through to the relics orbiting us now. But notice what it also does. It pushes the achievement of the early universe even further. We are no longer just saying the early universe made bright galaxies fast. We are saying it may have already been assembling dense, chemically enriched star clusters. The kind of structures that take real work to build, almost at the very beginning. Enrichment means earlier stars had already lived and died and seeded their surroundings. There were generations before this one, in a universe barely old enough to have any. Each layer we peel back reveals another step that had to happen even earlier. Stars, then clusters, then enrichment, then more stars, all stacked into a sliver of time that keeps looking too thin to hold them. And the chemistry was not even the strangest thing the light revealed. There was one more clue buried in the spectrum, one that touches not just this galaxy, but the state of the entire universe around it. It suggested that the great cosmic fog, the haze that filled all of space in the early days, had begun to lift far sooner than it should have. To understand the next clue, you have to know that the early universe was foggy, and that the fog had a schedule of its own. For a long stretch after the beginning, space was filled with a thin haze of hydrogen gas in a particular state. The atoms were neutral, each one holding onto its electron. Neutral hydrogen has a habit. It absorbs certain kinds of light, especially the energetic ultraviolet light that young hot stars pour out. So in those early ages, the universe was, in a real sense, opaque. Light from the first stars and galaxies tried to travel outward and ran straight into a wall of gas that soaked it up. The cosmos was glowing on the inside, but wrapped in fog. Then, gradually, the fog burned away. As more stars and galaxies switched on, their fierce radiation began stripping the electrons off the hydrogen atoms, turning the gas back into a state that lets light pass freely. Space cleared, region by region, like patches of morning mist lifting off a field, until the whole universe became transparent and stayed that way. This great clearing is one of the major chapters in the history of the cosmos, the moment the lights came on and could finally be seen. And it had a timeline. By every model we have, at the extreme distance of this newly confirmed galaxy, the clearing should barely have started. The universe at that point should still be drowned in neutral hydrogen, the fog almost completely intact, nearly every scrap of space still opaque. This is one of the firmer predictions in the field. That early, the fog should be everywhere. The light from this galaxy hints otherwise. Woven into its spectrum was a subtle feature, or rather the absence of one. When light from a galaxy this distant passes through surrounding neutral hydrogen, the fog leaves a particular mark on the light, a kind of bruise on one edge of it. In this galaxy, that mark looked weaker than it should. The team read it as tentative evidence that the gas immediately around the galaxy was already partly cleared, partly transparent, at a moment when the models insist it should have been almost solidly foggy. It is a careful, hedged result. The word the team used was tentative, and that honesty matters because a single faint feature in the light of one extraordinarily distant object is a thin thread to hang a conclusion on. This is not settled. It is a clue, flagged as a clue. But it points the same direction as everything else. The fog lifting early would mean that enough stars and galaxies had switched on and burned fiercely enough to start clearing space sooner than the schedule allows, which means more sources of light, earlier, more powerful. The same story again, told now not by a single galaxy's mass, but by the state of all the gas around it. So the pattern is no longer confined to individual objects being too big or too bright. It is starting to show up in the condition of the universe itself. The whole place may have woken up ahead of time. And if you want to know just how far ahead, you have to stop looking at single galaxies and pull back to take in the entire early sky at once. Because the real shock is not any one object. It is how many of them there are. Step back from any single galaxy and look at the whole early sky, and the deepest problem comes into focus. It was never really about one impossible object. It is about the sheer number of them. When the telescope first surveyed the distant universe, it did not find a rare giant here and there against a backdrop of faint smudges. It found bright early galaxies in abundance, far more than the models said should be there. And the further back it looked, the worse the mismatch became. At the most extreme distances, near the very frontier where this story now lives, the count is not off by a little. By the reckoning of the team studying that frontier, there are more than 100 times as many bright galaxies as the standard models predicted there should be. Not twice as many, not 10 times, more than 100-fold. Let that number sit. A model can survive being off by a bit. You adjust a few details, tighten an assumption, and the gap closes. Being wrong by a factor of 100 is a different kind of failure. It means that whatever you thought was happening in the early universe, the real thing was happening on a vastly larger scale. The cosmos was lit up, at its dawn, more than 100 times more brightly than our best schedule allowed. And this is the part that does not deflate. Earlier in the story, we watched the mass crisis soften. Careful work brought the heaviest galaxies down to size, showed that some of their light came from black holes rather than stars, and eased the worst of the panic about impossibly massive objects. The researcher who led that correction said plainly that none of them were so massive as to break the universe. But the same researcher pointed straight at what would not go away. Even after the masses were corrected, even after the worst case was tamed, there were still far too many of these galaxies. Roughly twice as many massive galaxies as predicted in her own careful study, and at the bright frontier, the excess balloons far beyond that. You can shrink the giants, you cannot make them rare. The early universe was simply crowded with bright galaxies in a way the model never anticipated. This is why the problem refuses to die. Every fix so far has chipped at the wrong corner. The worry was never really that one galaxy weighed too much. One overweight galaxy could be a mistake. The worry is that the entire early universe is glowing too brightly, with too many sources, too soon, and that pattern shows up no matter which patch of sky you point at. It is everywhere. It is the rule, not the exception. So the question we have been carrying since the first dim room has now grown to the size of the whole sky. It is not how did this one galaxy get so big? It is why is the entire early universe so much brighter and busier than every careful prediction said it could be. And faced with a mismatch that large, the field has not panicked. It has gone to work. Researchers have laid out a set of possible explanations, each one an attempt to close the gap without tearing down the whole model. Some are modest, some are radical. They run from a clever trick of timing, all the way to the suggestion that our picture of the universe itself is broken. The first explanation is also the gentlest. It says the universe is not making too much. It is just flashing brighter than we realized, in sudden bursts. The gentlest explanation does not require the early universe to build any more than the model allows. It only requires the building to happen in bursts, and bursts can play tricks on the eye. Picture a galaxy not making stars at a steady pace, but in fits and flares. For a stretch, it sits quiet, gathering gas. Then something tips it over, and it erupts into a furious episode of starbirth, lighting it with brilliant young stars all at once. Those young stars are blazingly bright, far brighter for their weight than older stars. So during the flare, the galaxy shines with a brightness wildly out of proportion to how much mass it actually contains. Then, the brightest stars burn out, the galaxy dims, and it waits for the next eruption. This flickering changes everything about how we read these objects. Remember the trap from earlier in the story? We do not measure mass, we measure light, and we convert light into mass using an assumption about what is shining. If a galaxy is caught mid-flare, gleaming with a brief surge of young stars, and we assume that brightness reflects a calm, settled population, we will badly overestimate its mass. We will see a flash and call it a mountain. So the bursts solve part of the puzzle for free. The early universe in this picture is not violating the ceiling on how much it can build. It is simply that the galaxies we happen to catch are the ones flaring, the ones briefly turned up to full brightness. We are seeing the universe at its loudest moments and mistaking the noise for size. It also helps with the sheer number of them. If galaxies flicker, then at any given moment, a chunk of them are mid-flare and easy to spot, while their dimmer phases hide. A telescope sweeping the early sky would naturally pick out the bright ones and overcount how many luminous galaxies there really are. Some of the 100-fold excess could be the selection at work, the bright phase catching our eye while the quiet phase slips past. This is an appealing answer because it asks for so little. It does not break any law. It does not require strange new physics or a rewritten timeline. It just says galaxies in the early universe were more volatile, more prone to violent surges of starbirth than the steady model assumed. And there is good reason to think that is true. The early universe was denser and more chaotic, gas piling in fast, conditions ripe for exactly these kinds of eruptions. Improved computer simulations, run with this burstiness built in, do reproduce more of what the telescope sees. They generate brighter galaxies, more often, without breaking the underlying rules. So this is not wishful thinking. It is a real effect that genuinely narrows the gap. But it narrows it. It does not close it. Bursts can inflate brightness, but they cannot conjure over massive black holes that have no business existing yet. They cannot fully explain a fog that lifted too early. And there is a limit to how much of the excess pure flickering can absorb before you are asking the burst to do too much work. The flares help. They are not the whole answer, which pushes us toward a stranger possibility. Maybe the problem is not when the early stars shone or how steadily. Maybe the problem is the stars themselves, and what they were made of, and how unlike anything alive today they truly were. The next idea reaches back to the very first stars, and asks whether they were a different kind of thing entirely. Every star you have ever seen formed out of gas that already carried a sprinkle of heavy elements, the leftovers of stars that lived and died before it. But the very first stars had no such inheritance. They condensed out of pristine gas, almost pure hydrogen and helium, with none of the heavier ingredients mixed in. And that pristine gas behaves differently. Without heavy elements to help it shed heat and cool down, the gas resists collapsing into small clumps. It tends instead to gather into enormous masses before igniting. The result, in theory, is a first generation of stars unlike anything in the universe today. Far more massive than ordinary stars, hotter, bluer, burning through their fuel at a furious rate and shining with a brilliance that dwarfs the steady stars around us now. A handful of these monsters could outshine a whole crowd of ordinary stars while weighing far less in total. You can see why this matters for our problem. If the early galaxies were lit by these huge, brilliant first stars, then they would pump out far more light per unit of mass than we assumed. And our whole mass estimate rests on that ratio, on how much light a given amount of star stuff produces. Feed in the wrong ratio, built for ordinary modern stars, and you overstate the mass. Swap in these blazing early giants, and the same brightness suddenly requires far less material. The galaxy shrinks back under the ceiling, not because it has fewer stars by weight, but because its stars are so much brighter for what they weigh. It would also help with the bright, clean light we keep seeing at the frontier. These first stars are intensely hot and shine strongly in exactly the kind of light that, stretched across the universe, lands in the telescope's view. They would make the early sky glow harder than a population of ordinary stars ever could. There is a catch, and it is a big one. We have never actually seen these first stars. Not one, not directly, not confirmed. They are a prediction, a well-motivated one, but still a prediction. They burn out fast. They sit at distances at the very edge of what we can reach, and catching their unmistakable signature has so far eluded every search. The chemical clues in objects like the distant galaxy we examined are tantalizing hints that such stars existed and enrich their surroundings. Hints are not the thing itself. So this explanation lives in an honest middle ground. It is a leading idea, grounded in solid physics about how pristine gas should behave, and it would tidily resolve a chunk of the brightness problem. But it leans on a population of stars we have inferred rather than observed. And until we catch one, it stays a strong proposal rather than a settled fact. Notice the shape of where we are. The burst said the timing fooled us. The first stars say the light itself fooled us. Both are ways of arguing that the galaxies are not really too massive, that we have been misreading what we see. They protect the schedule by blaming the measurement. But there is a bolder line of thinking that refuses that comfort. It accepts that the early universe really did build fast, and argues that our notion of how slowly galaxies must form was simply wrong from the start. The bolder argument stops trying to explain away the brightness and accepts it. Yes, it says, the early universe really did build galaxies fast. We were wrong about the speed limit. Go back to the ceiling we built so carefully near the start of this story. Part of that ceiling came from a single stubborn number, the fraction of a galaxy's gas that ever becomes stars. In the galaxies we measure today, that fraction is small. Only a few % of the available gas ends up as stars. The rest gets blown out by exploding stars, heated, scattered, wasted. We took that small fraction and assumed it held in the early universe too. That assumption is what made the early giants look impossible. This argument says that assumption was the mistake. In the early universe, conditions were different in a way that matters. Everything was packed closer together. Gas was denser and fell inward harder and faster. And crucially, the process that normally chokes off star formation, the violent feedback from dying stars blowing gas away, may not have had time to take hold. Star birth could have run ahead of its own brakes. Think about why galaxies waste so much gas today. They make stars. The biggest of those stars die in explosions. Those explosions push gas out, and the loss starves future star formation. It is a self-regulating cycle, and it keeps efficiency low. But that cycle takes time to kick in. The stars have to form, leave, and die before they can blow anything away. In the dense, fast-moving early universe, gas could collapse into stars more quickly than the explosions could clear it out. For a window, the brakes were off. The galaxy could turn a large fraction of its gas into stars before it ever began wrecking its own supply. Crank that efficiency up, and the math changes completely. A halo that, at low efficiency, could only make a modest galaxy can, at high efficiency, make a far brighter and more massive one from the very same amount of matter. You do not need extra dark matter. You do not need to break the budget on how much normal matter exists. You just need the early universe to have been far better at converting gas into stars than anywhere we see today. The ceiling rises not because the rules changed, but because we had filled in one of the numbers wrong. This is in many ways the most satisfying answer, because it keeps the entire framework intact. The standard model of the universe survives. Dark matter still builds its scaffolding on schedule. The amount of normal matter stays exactly as measured. The only thing that changes is a detail about how galaxies behaved in their first chaotic moments. And that detail is one we could plausibly have gotten wrong, since we have never had a clear look at that era until now. When researchers build this higher early efficiency into their simulations, the simulated early universe starts to look more like the one the telescope actually shows. Brighter galaxies, more of them, sooner. The gap shrinks again. And yet, even here, the resolution carries a quiet warning. To make it work, the early universe has to behave in a way no later era does, with star formation running almost unchecked. That is itself a strange claim about a place we cannot visit. We are explaining one surprise by proposing a different, hidden surprise, which leaves the door open, just a crack, for the most radical idea of all. What if it is not the galaxies, or the stars, or the efficiency? What if it is the clock? Every explanation so far has tried to save the schedule. The boldest idea gives up on saving it, and asks whether the schedule itself, the timeline of the universe, might be wrong. This is the option scientists reach for last, and for good reason. The standard model of the universe is not some fragile guess. It has passed test after test for decades. It predicts the leftover heat of the beginning, glowing across the sky. It predicts how galaxies cluster into vast webs. It predicts the precise mix of the lightest elements forged in the first minutes of creation. To question it because of some early bright galaxies, when gentler explanations are still on the table, would be reckless. Most researchers do not go there, and they are right to be cautious. But a few have started asking the question anyway, quietly, because the model already has a couple of unrelated cracks in it. Places where careful measurements disagree with each other in ways no one has fully resolved. When a building has a few existing cracks, and then a new strain appears, you are at least allowed to wonder whether the foundation is the problem. The radical proposals take a few forms. Some suggest that the early universe expanded on a slightly different schedule than the standard model assumes, perhaps driven by a burst of some extra ingredient pushing things along in the first stretch after the beginning. Shift the early timeline even a little, and you change how much time galaxies had to form, which could buy them the extra room they seem to need. Others propose subtle changes to how gravity itself behaves on the larger scales, which would alter how fast the dark matter scaffolding could pile up. If the scaffolding grew faster than the standard model allows, the galaxies built on it could grow faster too. These ideas share a heavy burden. Any change you make to the early universe to explain the bright galaxies must not wreck all the other predictions the model gets right. That is an extraordinarily tight constraint. You cannot just loosen the timeline to suit one problem and ignore the leftover heat of the beginning, or the cluttering of galaxies, or the mix of light elements. A new model has to thread every one of those needles at once. Most attempts fail that test immediately. The standard model is hard to beat precisely because it explains so much. So this remains very much a minority view and an open mystery rather than a leading answer. The honest state of things is that the bright early galaxies are not yet, on their own, strong enough evidence to overturn the model. Almost everyone in the field expects the gentler explanations, the bursts, the strange first stars, the higher efficiency to carry most of the load. The clock is probably fine, probably. The word does a lot of work there, because the reason a few serious researchers keep the radical door open is that the telescope keeps pushing the frontier back. And at the frontier, the mismatch keeps growing rather than shrinking. As long as the surprises pile up faster than the gentle explanations can absorb them, the possibility that something deeper is wrong cannot be fully dismissed. And there is one more place to look for that deeper wrongness. The strangest frontier of all. It involves the part of the universe we understand the least. The invisible matter that makes up most of everything. Some researchers think the key to these early giants may lie not in the stars we can see, but in the dark stuff we cannot. The strangest line of thinking points at the part of the universe we understand the least. Most of the matter out there is dark, unseen, known only by its gravity. What if that dark matter is not the simple, inert scaffolding we have been treating it as? What if it played an active hand in building the early giants? Throughout this story, dark matter has had one job. It clumps into halos, and its gravity pulls in the gas that makes stars. Quiet, invisible, structural. But we do not actually know what dark matter is. We only know how it pulls, and that ignorance leaves room for it to be stranger than we assumed, and to do more than just sit there providing gravity. One family of ideas imagines dark matter made of particles so light and so spread out that they behave less like grains and more like waves, pooling into smooth, dense cores at the centers of halos. Such a core would act like a funnel, channeling gas inward fast and hard, concentrating it in exactly the way you would need to build a dense, bright object, or to seed an enormous black hole far more quickly than ordinary gravity alone would manage. The early overmassive black holes that broke the rule tying them to their galaxies might be born inside these dark cores, given a violent head start by the very stuff we cannot see. Another family imagines dark matter that can bump into itself, interacting in a way the simplest models forbid. Dark matter that collides and exchanges energy would clump differently, building dense central regions that could likewise funnel gas and seed giants ahead of schedule. The demographics of these early black holes, how many there are and how heavy, might then become a way to probe what dark matter actually is, turning the mystery of the giants into a clue about the deeper mystery of the dark. And there are stranger proposals still, out at the speculative edge, where some researchers wonder whether the very first luminous objects were not ordinary stars at all, but enormous diffuse structures powered by dark matter itself, glowing not from nuclear fire, but from the slow release of energy as dark matter particles meet and annihilate deep inside them. Such objects, if they ever existed, could be huge and bright in ways no ordinary star could match. and could leave behind exactly the kind of heavy black hole seeds the early universe seems to demand. Hold all of this lightly. These are proposals, not findings, sitting at the frontier of theory where ideas are tested against the data and most quietly fail. No one has shown that dark matter does any of this. The simplest version, the quiet structural one, still works for almost everything we observe. These exotic ideas earn their hearing only because the early universe is showing us things the simple version struggles to build fast enough. But there is something fitting about where the search has led. We went looking for why the visible universe is too bright and too built up too early. And one of the roads out of the puzzle runs straight into the invisible majority of everything. The dark matter we have never identified. The thing we cannot see may be the thing that built the things we cannot explain. So now we have the full spread of answers laid before us, from the gentle to the radical. It is time to be honest about which of them is winning, what has actually been settled, and what still stands unexplained after all the scrutiny. Because the picture is neither as broken as the first headlines feared, nor as safe as anyone would like. After all of it, the panic and the corrections and the wild proposals, it helps to sort calmly through what survived. Because the truth sits between the two extremes, and both extremes are wrong. Start with what did not break, because this is the part the early headlines got wrong. The universe is not shattered. The most frightening reading, that galaxies impossibly heavier than the matter budget allows were sitting in the early cosmos, did not hold up. Careful work brought the giants down to size. Much of their excess brightness turned out to come from black holes glowing at their centers, not from impossible crowds of stars. The standard model of the universe, with its dark matter scaffolding and its measured budget of normal matter, still stands. It still passes every one of the great tests it always passed. No single galaxy has yet been confirmed so massive that it forces the model to its knees. The cautious researchers were right. The universe breakers, in the end, did not break the universe. That is the reassuring half. Now the other half, the part that did not go away, no matter how hard it was pushed. There are still far too many bright galaxies in the early universe. Shrinking the giants did not make them rare. At the frontier, the excess runs to more than 100 times what the models predicted, and that abundance is real and stubborn. The overmassive black holes are still there, still too big for their galaxies, still demanding to have been born huge or grown impossibly fast, with no fully settled explanation for how. The clean, dense, blazing little galaxy at the very edge of the observable past is confirmed beyond argument, too bright and too early for comfort, and the hint that the cosmic fog lifted ahead of schedule still hangs in the data, waiting to be confirmed or dismissed. So the honest accounting is this: the catastrophe was downgraded to a deep, genuine puzzle, not a broken universe, but a universe that is consistently, measurably ahead of where our best models said it should be. The leading explanations, bursts of star birth, strange, brilliant first stars, and early galaxies that turned gas into stars with unusual efficiency, are doing real work and closing much of the gap. The radical ideas about the timeline and about exotic dark matter wait in the wings, mostly unneeded so far, kept alive only because the frontier keeps surprising us. What you should take from this is not that scientists cried wolf, it is the opposite. You watched a field do its job in public. A shocking result came in. People raised the alarm honestly, called their objects candidates, and said out loud that they might be wrong. Then they spent the following stretch of time testing themselves as hard as they could, shrinking the parts that were overblown and refusing to let go of the parts that survived. The result is not a tidy victory or a clean defeat. It is a sharpened mystery, with its real edges finally visible. And once you see those real edges clearly, something clicks into place. Look back across everything we have walked through, the galaxies, the black holes, the chemistry, the fog. They are not separate surprises. They are the same surprise, wearing different clothes, repeating itself everywhere we look. There is a single pattern running under all of it. And naming that pattern is what turns a pile of anomalies into one clear, unsettling fact about the universe we live in. Lay all the pieces side by side, and the same shape appears in every one of them. The galaxies were brighter and more built up than the schedule allowed. The black holes were more massive than their galaxies should permit, and grew faster than feeding should allow. The chemistry showed dense star clusters already enriched by earlier generations, in a universe barely old enough to have any. The fog seems to have lifted sooner than the models predicted. Every single anomaly in this story points the same direction. Earlier, faster, more. The early universe did everything ahead of when it was supposed to. That is the pattern. Not one broken rule, but one consistent direction of surprise. Across galaxy formation, black hole growth, star birth, chemical enrichment, and the clearing of the cosmic fog, the real universe runs ahead of our best timeline. It woke up faster than we thought a universe could. And here is the thing that pattern reveals about us. Every prediction that got beaten shared a single hidden assumption. We assumed the early universe was slow. We pictured a patient, gradual dawn, faint things slowly gathering into bright things over long stretches of time, because that is how building works in the universe we are used to. We took the leisurely pace of the cosmos around us today and ran it backward, and assumed the beginning was just a slower, dimmer version of now. That assumption is what the telescope has been demolishing, piece by piece. The early universe was not a slow, dim, gradual place. It was fast, dense, violent, and bright. It made stars in furious bursts. It built black holes at a sprint. It assembled dense clusters and enriched its gas and lit itself up. All in a window of time we kept insisting was too short. The slowness we expected was never out there in the cosmos. It was in our model of it. This is why the gentle explanations work as well as they do. The bursts, the brilliant first stars, the high efficiency, they are all really the same correction stated different ways. They all say the early universe was more energetic and more productive than we assumed. They are not separate patches on separate holes. They are one repair to one mistaken idea, that the dawn was calm. And it is why the radical ideas, the wrong clock, and the active dark matter cannot be fully dismissed even as they wait in the wings. If the universe keeps running ahead of us as the telescope pushes deeper, at some point the gentle corrections may not be enough, and the direction of every surprise is already pointing past them towards something more fundamental. The pattern itself is a warning. When reality consistently beats your model in the same direction, the model is missing something real. So the thing the telescope found that is bigger than physics says can exist was never really a single object. It was a fact about the whole early universe. It built more and built it faster than our deepest understanding allowed. Not impossibly. Not in a way that shatters the laws, but far enough beyond our expectations that we have had to rebuild our picture of the cosmic dawn from the ground up. And the rebuilding is not finished because the telescope is not finished. It is still looking. It is still pushing the edge of the visible past further back. And the closer it gets to the very first light, the more the pattern matters, and the more pressing the unanswered question becomes. The story does not have an ending yet, because the instrument that started it is still working, still pushing the edge of the visible past further into the dark. That is the part to hold on to. We are not looking back at a closed chapter, tidied up and filed away. The frontier is moving in real time. The most distant confirmed galaxy is a record that the people who said it fully expect to lose, and soon. They said as much. They wrote that the telescope appears poised to drive the boundary back again and again toward distances that until recently seemed unreachable, close to the era of the very first stars. The edge is not a wall. It is a tide line that keeps receding as we learn to see further. Think about what sits just beyond the current edge. We have been studying galaxies from a few 100 million years after the beginning. But somewhere deeper still, earlier still, lies the moment the very first stars switched on in a universe that had never held a single point of light. We have never seen that moment. It is the true cosmic dawn, the instant darkness ended. And for the first time, it no longer feels impossibly far. The telescope is closing in on it. More instruments are coming too. Another great space telescope is being readied, designed to sweep across enormous patches of sky, rather than peer at tiny ones. Built to find these distant, rare objects by the thousands, rather than one at a time. Where the current telescope finds a handful of giants and studies them in depth, the next will census whole multitudes of them and turn this collection of startling individual cases into hard statistics. We will go from asking whether the early universe is too bright to measuring exactly how much, exactly where, exactly when. And here is why that matters for everything we have walked through. Right now, the gentle explanations are winning, holding the line, absorbing most of the surprise. But that balance depends on the size of the mismatch, and the mismatch keeps growing as we look deeper. Every time the frontier moves back, the early universe shows up brighter and busier than the step before. If that trend continues, at some point the gentle fixes run out of room, and the harder possibilities, the ones waiting in the wings, get pulled onto the stage. So the question we have carried since the first dim room is not closing. It is sharpening, and it is getting more urgent the deeper we see. How did the universe build so much, so fast, so early? We have better pieces of an answer than we did at the start. We also have a clearer view of exactly how much we still cannot explain. The telescope handed us both at once, the partial answer and the deeper mystery, and it is still handing us more with every distant galaxy it confirms. We are living through the part of the story where the map is being redrawn. Not the calm afterward, when it is all settled and explained in a textbook, but the strange, unfinished middle, where the old picture has cracked and the new one is not yet built. The cosmic dawn is being rewritten in front of us, and no one yet knows the final shape of it. Which leaves one last thing to face. Not what this means for the models, or the telescopes, or the distant past. What it means for you, sitting here, made of the very matter that all of this is about. So return to the question we started with. The one the people in that dim room could not shake. They went looking for the faint, slow beginning of everything, and instead found galaxies too bright and too built up to fit the rules. The question was simple and terrible. Either the rules are wrong, or something out there is. Here is the answer, as honestly as it can be given. Nothing out there is wrong. The galaxies are real. The black holes are real. The blazing little speck at the edge of time is confirmed and exactly where it appears to be. Not one law of physics has been caught breaking. The universe is behaving precisely as the universe behaves. The thing that was wrong, the only thing, was our assumption about how slowly it all had to happen. That is the real discovery hiding inside the title. The telescope did find something bigger than physics said could exist, but the ceiling it crashed through was never the universe's, it was ours. We had drawn a low, slow line over the cosmic dawn and called it a law, and the universe simply rose past it, faster and brighter than our imagination had allowed. The limit that broke was a limit on what we believed the beginning was capable of. And now, bring it home. Because this is not a story about distant lights. The atoms in your hands, the iron in your blood, the calcium in your bones, every heavy thing you are made of was forged inside stars and scattered when they died. That forging had to start somewhere. It started in exactly the era this telescope is now staring into, the fast, violent, overachieving dawn that built more than we thought it could. You are downstream of that hurry. The reason there has been enough time across the long age of the universe to build stars and planets and the particular arrangement of matter that is reading these words is that the universe got started early. It did not dawdle, it raced. The light from that race is still arriving. It is falling on a telescope 1,000,000 miles from Earth right now. Light that left when the universe was a few 100 million years old. Light that shows a cosmos already awake and shining when our oldest models said it should still have been dark and cold and slow. That light has been traveling toward this moment for nearly the whole age of everything. And it carries a single message, written in galaxies that should not have existed yet. The universe was never as patient as we are.